Okay, off we go. So last time, this is where we were. We were talking about vector surface integrals. By the way, a little terminology thing. So vector surface integrals, where did they come from? They came from us trying to figure out how to use, frankly, the idea of a scalar surface integral to understand flux. Right? So flux is what we were actually working on. And out comes this new construction that we had to recognize is different from a scalar surface integral after all. Anyway, since flux is the motivating construction, sometimes these are called flux integrals. So anyway, heads up on that terminology. I'll probably, reflexively use that term here and there. Anyway, so what we saw last time is that because we've already set up all of this development here of how to use a parameterization to relate input areas to output areas, and we know the stretching factor, and we've got it all this development done. And in particular, we had this, which we plug in here. Right? And having done that, and I'm going quickly because we did this last time, I put the asterisk on the, I think, fairly persuasive rhetorical argument that I've made about, hey, these look like they ought to be equal, right? I mean, both of what I have circled in blue, correct me if I'm wrong, point in the same direction as capital N and have the same magnitude as capital N. Right? It kind of feels like these ought to be the same. And then I think that's about where we ran out of time. Or let's see, wait, did we do this example last time? Maybe we did. I think we did. Yeah, okay, right. Okay, anyway, so point is I just used that formula, right? This is the pullback formula for computing a flux integral, right? Vector surface integral. And, this is a very doable calculation right there, and it's just a matter of multiplying it out, and it's an integral of a polynomial. Okay, all right, so what was the problem with this, right? I was making a very dramatic deal about something that seems pretty clear. And here's the problem. When I made this statement, I was ignoring subtle issues of orientation. And orientation's really important. Right? And we've seen this in a couple different ways. For one thing, when you're computing a vector line integral, you better get the orientation right. Right? In other words, it takes a lot more work to drive up a mountain road than it takes to drive down the mountain road. I mean, that's an important difference. You can say it's just a minus sign, but it's a big actual difference in terms of, reality. So, very important. And there's something very analogous going on here. So here's the issue, and we've talked about everything on the page here at kind of different times, though. So we started with this idea of an oriented surface. Here's a surface, right? And keep in mind, if we're going to call it an oriented surface, it has to have an orientation unit normal, right? So some choice of which direction through the surface we're going to call the positive direction through the surface. And it could be either. There's no magic laws that say, upward is always positive or anything like that. Not at all. No. Whatever. You can orient a surface however you want. Appropriate to your circumstance. Right? So, kind of whatever. All right. Secondly, let's see here. Let me clean up the drawing a little bit here. Okay, so we have our orientation unit normal. That's like that. But secondly, don't forget, when you parameterize, in the process of parameterizing, that causes these partials to be whatever they're going to be, which causes capital N to be whatever it's going to be, which then causes what we call the parameterized unit normal to be whatever it's going to be. And that, again, comes out of the parameterization, which we made up kind of arbitrarily. And, think back to the various parameterization methods that we talked about, right? The graph parameterization method, there's the coordinate system, approach, you might call it, and then deforming, blah, blah, blah. None of them are paying attention to how you're orienting the surface. They're just we're just trying to get something on the page. We're just trying to come up with some algebra that will produce points on the surface. So when you create the parameterization, and implicitly then when you inadvertently create this parameterized unit normal, it's a coin flip as to whether you oriented in the way you were supposed to. We were supposed to orient according to whatever the given orientation of the surface is. And we just kind of, okay, I'm going to parameterize that way, and we just pick one. Literally a coin flip as to whether you'll get it right. All right, so that's what I did wrong on the previous page. I was assuming, well, again, I did this on purpose for dramatic purposes. I swept under the rug that it's not fair to assume that these two orientations are the same. It's just not fair. Right? So how this showed up in the algebra, and again, here's a kind of a reproduction of that little bit of algebra, and I'll remind you, I looked at these two things, and I say, hey, it looks like a duck, quacks like a duck, right? These have got to be the same vector. Well, this one is a unit normal times its magnitude. Yeah, sure, but only if you're understanding this as the parameterized unit normal, whereas this one that we actually are dealing with is the orientation unit normal. And you, again, cannot assume that those are the same, and therefore you cannot assume that this step is valid. When you take this step here, you might be off by a minus sign. So that's the problem. Now again, it's subtle, right? This is a lot more noticeable when you're talking about line integrals. And there's a good reason for this. If you think about, when you parameterize a curve, right? How do you parameterize a curve? Well, we think of the parameterization as being based on time. We think of t as being time. So when you parameterize, it's like you can almost see in how you write down the algebra what direction that parameterization is tracing out the curve, which means you can kind of see the orientation. I don't want to say it's obvious, but it a lot easier to, at a glance, just kind of notice which direction you're parameterizing. We have the same problem here, it's just harder to notice. Right? And so again, very subtle. A lot of people miss this. And again, the question is not whether you were only off by a minus sign. The question is whether your bridge falls down. Right? And if you get this minus sign wrong, well, again, you're only off by a minus sign, but what that means is the answer that should have been this is actually this, and yes, they are negatives of each other, but this is a big problem in between. Right? So it's a very important point. So we have to distinguish the ds vector, which is oriented as the surface is given, versus the formula that we use to compute it, capital N du dv, that is oriented according to your arbitrary parameterization. We got to recognize those may or may not be same, and so don't forget to think about that. And there's a possible minus sign in here that you're responsible for. Okay, now here's the good news. If you get it right, everything's fine. And by the way, that's what happened in this first example that we did, right? So I felt a little guilty while we were doing this, but in fact, we got the orientation correct here. I totally swept it under the rug, again, for dramatic purposes. But we were given that our surface is oriented upward, right? Says so right there. And then when I parameterized, that led to a parameterized orientation, which is also clearly upward, right? And so, is the given orientation consistent with the parameterized orientation? Yep, in this case it was. Everything's fine, no problem. This calculation goes through no issues, because I got lucky on the coin flip. What we're going to see now is an example of how it will look if you get it wrong, and how to deal with it if you get it wrong. And again, coin flip. Could be, you never know, right? So you have to be on the watch out for this. Okay, so this example here, now you're going to notice it's a very, very, very similar looking example. It's the same vector field. It's the same surface, in particular the same portion of the same surface, everything's the same, except now the given orientation is downward. Perfectly reasonable question. Again, there's nothing magic about upward being positive or anything like that. So this is, we're interested in the downward flux, aka the flux through the downward oriented surface. Okay, I mean, what do we do about the downward? How do I factor in the fact that I'm supposed to orient this downward as I parameterize? And here's the sort of surprising answer: you don't. Ignore it for the moment. Just for the moment. Parameterize however you want. For the moment. And then we'll check and see if we got it right, and if we got it wrong, we'll fix it. So I'm going to parameterize with the graph parameterization again, right? And yada, yada, yada. Compute the resulting capital N, and notice this vector is oriented upward, not downward. Right, so here I have to recognize I got it wrong. Now, again, I don't know how to parameterize deliberately so that I will know for sure that I'll get it right. It's not my fault, right? But it remains. Independent of whose fault it is, I got it wrong here. I was supposed to parameterize downward. I inadvertently parameterized upward. These are not consistent. And here's the good news. Even though I got it wrong, we parameterized upside down. Okay, well, all that means is that everything is off by a factor of exactly a negative, which means that my result is off by exactly a negative, and I just fix it by throwing in a minus sign. And it's as convenient as that. I just want to try to get this all onto the page here. Here we go. So, what you're going to do on an exam, first of all, make sure to remember to pause when you finish computing your capital N. This is very important. You got to pause, and you got to remember to ask yourself the question, hey, I have to worry about whether I parameterize this the right way, and you got to actually think about that and figure out what you did. So just recognize that we parameterized it upside down. I mean, how you phrase that, you can just do it like I've done here, kind of circle the inconsistency and say, whoopsie, right? Totally fine, right? No problem. And then just insert the minus sign to fix it and keep on trucking. It's easy to deal with, right? That's the good news. Totally easy to deal with. The hardest part about this orientation business, aside from understanding what we're talking about in the first place, is remembering to check. So you gotta, I don't know how to tell you to help you remember things. Try to develop a habit. Do several practice problems where you have to stop at this point, and of course, one thing I try to do is I make a big deal out of it in class, and the bigger deal I make out of it, the less of this kind of mistake I see on exam papers. But we got to make sure to remember, and then just fix it with a minus sign. Nothing to it. Now, there is a little detail double that is important. You do have to be careful with. And that is, where do you insert the minus sign? And this matters. Keep in mind, what we're interested in this course is not whether you get the correct answer at the bottom of the page. That's not what this class is, right? This class is about mathematical ideas and mathematical reasoning. And so your argument to get down to that answer is most of where points come from. So you have to insert the minus sign in the correct place. Now in this case, we were asked to compute a flux. ds is defined based on the given surface orientation, right? The given orientation of the surface you start with. What we replace it with here, this n ds dt, is not. That's oriented based on how you parameterized, right? And then on down the line, this is literally just a recopy of what n is, and so that comes from based on how you parameterized. So it's important that you put this minus sign in the correct place. Notice I am here, because of that minus sign, recognizing that green and blue are not the same. And because that minus sign continues, of course, right, I am in the next step, implicitly just, rewriting capital N. I have two true statements here. Now let me show you what goes wrong if you put the minus sign in the wrong spot. Now this is going to seem fussy, right? I get that, right? But this is very much not fussy. If you don't put the minus sign here, if you just kind of forget about that minus sign. In fact, let me do this. I'll just kind of, why isn't that working? I don't know why that's not working. If you don't put that minus sign there, hypothetically, right? Well, what you're saying then is that these two opposite-oriented things are the same. That is not true. That is a false bit of mathematical reasoning. And again, mathematical reasoning is what we're here for, right? So the fact that we got that minus sign in the wrong spot made us write down something that isn't true. It also, by putting the minus sign here, but not previously, notice now we again have a problem, right? I'm again basically saying that these two blue equal objects are negatives of each other. That is also false. And again, not okay, right? This is not, that's not how you do mathematical reasoning. Now, will you get the same answer at the end? Well, yeah, of course. Same answer in a box at the bottom. And again, not what this class is about, right? So please be careful about this. This really does matter. And make sure to think in terms, the way you resolve this, very simple matter, think in terms of what objects that you've written down in your algebra are oriented based on the givens, and what that you've written down is oriented based on the parameterization. And of course, it is where you switch from one to the other that you have to put the minus sign. Is that all right? Everybody okay with that? That makes sense? Okay. All right. Okay, I'm sure you noticed some sloppy language that I was using. This is, I don't want to say unavoidable, but it's almost unavoidable. It's certainly not conveniently avoidable. But the orientation was given as downward. And correct, this is not downward because that's positive. But it's not exactly straight upward either. And if I had oriented this the other way, if I had parameterized, if I had done a different, if I had done a different parameterization and that led to, the opposite orientation, that's not perfectly straight downward either. So, how's that okay? Let me explain what's going on here. This is a situation in which mathematical terminology is a little sloppy, but for good reasons. So let's consider a geometric sort of take on this, and let's look at this first surface right here. Let's look at this paraboloid. I'll tell you what. Let me do that in the pencil. I think it'll be easier to see. Oh gosh. So here's a paraboloid. And there are two possible orientations. Keep in mind an orientation is a choice of normal vectors. So green is one of my options, and blue is another one of my options. Those are really only two different ways to go through the surface. Right? One is the green, the other is the blue. When you describe these orientations with language, your goal is not to give a perfect description. We got algebra for that. We will do that with the algebra as needed, right? That's algebra's domain. When you describe these orientations with language, your goal is simply to distinguish unambiguously between the two options. Right? So let's think it through now. Let's look at this possible description I could describe, say, let's talk about the upward orientation. Which one of these could I possibly mean when I say upward? And I claim that this is pretty unambiguous, because with the green vectors, every single one of those green vectors is at least somewhat upward. Mostly not exactly perfectly straight upward, right? But they're at least somewhat upward. None of those green vectors point in any sense downward, right? Whereas, let's think about the blue orientation. None of those vectors are in any sense upward. They're not perfectly straight downward, but they're definitely not in any sense upward. Right? So when I say the word upward, again, that's not a perfectly, exactly perfect description of either orientation, but there's only one that I could possibly mean by that language. Does everybody see what I'm talking about there? Right, so this removes the ambiguity. There's no way, if I say upward, there's no way you're thinking the blue orientation. Right? Okay, so this is the job of the language. Okay, it doesn't need to be exact. It must be unambiguous. It must remove doubt as to what you're referring to. And that's kind of all you need to worry about. Now, the bad news is every circumstance is different. You really do have to tailor your language to the circumstance. So, for example, let's look at, let's look at this surface, this sphere. And again, there's two different possible orientations. Okay, there's that green one, and then there's this blue one. Wish I were faster. Okay, again, two orientations, two different directions through the surface that you can choose. Can I use the same language that worked out so well above? Can I call these two upward and downward? And I claim no. That's terrible. Upward, I don't even know what upward would mean. The language upward describes some of the green vectors, at least a little bit, but it kind of eliminates the other half of the green vectors. Upward does not really describe the green orientation very well at all. And likewise, with the blue orientation, it describes some of the blue vectors, or, somewhat upward, right? But it eliminates, is inconsistent with the other blue vectors. So this language here doesn't remove ambiguity at all. Upward doesn't help me in any way. What does help me is inward versus outward. And let's see, my colors are all mixed into here. I'm sorry, I'm just going to have to delete all this. But if I say inward, all of these vectors here are inward. None of these vectors are in any sense inward. Inward's got to be referring to the blue orientation. Again, ambiguity completely removed. Everybody happy? So you got to always tailor your language to the circumstance. Tailor it with this point in mind. Your goal is to remove ambiguities, and you got to think appropriately geometrically while you're doing it. Okay, so heads up on that. Okay, another example to look at the bottom. Y'all can look at on your own time. Proceeding along, now when we were talking about vector line integrals, we saw at least one example, maybe two, I don't remember, of geometric coincidence, geometric good fortune, where sometimes stuff just works out really nicely and you don't have to parameterize and deal with algebraic inconvenience. By the way, that is what we would be facing here in this example. If you were to parameterize this sphere, just think to yourself, wait a minute, how do I parameterize spheres? That's spherical graph parameterization. It's going to have a lot of trig. X, Y, and Z are going to be chock full of trig. Now look at the vector field. Chock full of X, Y's, and Z's. So that vector field is going to turn into a trig nightmare. The ds vector is going to be computed by, taking partials and then doing a cross product of a trig nightmare, which is going to make another trig nightmare. This is going to be a trig catastrophe if we brute force, plug and chug, pull back through a parameterization. So the lucky break to realize here, again, geometry is the big win here. When we say oriented outward, of course, that tells me outward, tells me a bunch of vectors like this, and keeping in mind that we're talking about a sphere. And keeping in mind that spheres are awesome. Spheres have lots of geometric symmetries in wonderful ways. And one of them is, if you have a sphere specifically centered at the origin, then the position vector, I'll use orange. The position vector from the origin to a point on the sphere is always parallel to the normal vector to the surface. And spheres centered at the origin are the only surfaces that have this feature. And at that point, since I know R and N, another typo. I'm sorry. By the way, anytime y'all see X vector representing X, Y, Z, that should be R. And I believe I got the great majority of those. I went through painstakingly, using my eyes, right, and tried to notice and fix all of them, and it looks like I've missed another one here. So I'll get that fixed at some point. But make a note, please, if you would, that X just means R. So that should be R. Okay, because of the fact that I know that the R vector and the N vector are parallel, and I know the N vector has magnitude 1, and I know the R vector is a radius, so it has magnitude 3. So, divide it by 3. Boom. There's your normal vector. Okay, now is this helpful? Well, it depends. Very often, very often it won't help. But it does help in this case. And it helps in this case because my normal vector there and my field vector there, well, if you just punch up that dot product 0, drop the pen, walk away, we win. No fuss, no fuss. Now that was lucky, right? I mean, I'm not saying that this is always going to work. I mean, I had to craft a field that would have this feature, right? In many cases, when you do this kind of thing, the dot product's not going to be 0, and now you've got an expression that involves X, Y's, and Z's, and, well, you're just going to have to parameterize, right? So I'm not saying this is a magic trick that will always work. I am saying that sometimes, and probably more often than you would expect, this kind of good fortune happens. And again, y'all are mostly engineers. It's not that different from physics, and I took a ton of physics classes, and I think you're going to have a similar experience. A very sizable fraction of the integrals that I experienced. Stuff like this. 10% maybe, right? Maybe not as much as symmetry. Symmetry is the best one, I think. But something on the order of 10% of the integrals that I saw. Geometric insights like this, boom, problem disappears. So please be on the lookout. This is a very, very cool tool for your toolbox. Notice again, this trick does not announce itself, right? And it won't be announced on exams. Hey, by the way, use the geometric trick here, because that's not how life works, right? And when y'all experience these kinds of integrals in the wild, right, like I did all those years ago, they were unannounced. It was just, well, here's the integral. This is what came up in the problem that was described in some other way, and no label that says, here's how you do this one, right? So be on the lookout for this kind of thing. Specifically, a tip-off is that if you have a nice surface, so spheres are pretty great and are full of fortunate symmetries. If you see a sphere, Yeah, be thinking in these terms. Planes. Also, nice, right? It's real easy to write down the normal vector given a plane. Nothing to it. You don't necessarily have to parameterize, and you might get lucky. So things like that. Be on the lookout. How we doing? Everybody okay? All right. Okay, here's another example. Different kind of geometric good fortune. This one with a plane. So we have this plane y equals 3, and what we're interested in is the part of that plane that satisfies a certain inequality. And y'all may recall we've dealt with something kind of like this at some point in the past. I think it might have been a homework exercise, but x to the 4th plus z to the 4th equals 1 is a round-ish thing. It's not a circle, but it's kind of halfway between a circle and a square. It's kind of a hybrid sort of curve, kind of like that. Okay, so that's our surface. And because it's inside of this plane, a couple of really great things happen. Just automatic freebies. One of them is, it's pretty clear what the normal vector is. Right? Again, its normal vector is perpendicular to the surface. The surface is in this plane. So it's going to be 0, 1, 0. Real quick, let's think about orientations. It does say, as it must, if you're going to talk about a flux, the surface has to be oriented, and it says here in the positive y direction, which I see this is. If it had said negative y direction, then it'd be 0, negative 1, 0. So boom, free normal vector. That's awesome. I don't have to, go through a process to find that normal vector. It's just boom. Sometimes a fish jump in the boat. Is that cool? Everybody happy? Okay, there's more that comes out of this because of the fact that we know we're only interested in points on this surface. Every point on this surface is in this plane, and this plane has y equals 3. I get to plug in y equals 3 everywhere that it shows up in the vector field because y is 3. Literally, for all the points that we're interested in. And notice this second coordinate, right? That second coordinate, when you plug in y equals 3, is 0. So I get to simplify the vector field a little bit. Again, just, quick observation. Just, hey, check it out. Boom. And then almost free, just writing it down. Again, because of the geometry, because it just happened to be that this is a geometrically convenient surface. Is everybody good with that part? Okay. So, these observations together, now again, this was a highly manufactured example, trying to make a sale here, but this kind of thing really does come up. Usefully, maybe not this usefully, right? But pretty usefully in some form or another, fairly often. Definitely worth being on the lookout for. And as a result of the combination of factors, this dot product, again, ends up being 0. So our answer is 0. And again, we drop the pen and walk away. And didn't have to parameterize. Didn't have to do the ensuing algebra. Didn't have to deal with the resulting pullback double integral. Just poof. Okay. All right. Okay. More stuff for y'all to read on your own. Again, I'm going to hit some highlights. This is, again, by the way, this might look familiar. Remember we talked about coordinate line integrals, and it ended up just being an alternative notation that frankly isn't even all that convenient. But you have to know it because it's in use, and it's in use because it's extremely powerful, or at least things like this are extremely powerful in other ways that are beyond what we're going to do in this course. So because it's powerful, it is popular, and because it's popular, you're going to see it. And so you have to know how to deal with it. This is what I'll call a kind of a liability for y'all. This is not going to help you solve any actual problems, but this is something that you have to know how to deal with because other people are going to be using it for their own reasons. So same kind of a deal. We just take an expression that we already had written in vector form and just write it out in coordinates. Right? You can take these partials and literally just write them out in coordinates. And you can take, this cross product and crank it on out. And we previously observed, oddly, unexpectedly, eyebrow raiser, that these coordinates of that cross product happen to be two-dimensional change of variables stretching factors. So weird, right? And now again, I made this observation before and I was just like, huh, wild. And then we just kind of moved on. Here's where we're going to actually kind of do something slick with this. And that is looking at where it is in the algebra and just distributing the ds dt like so. Right, no big deal there. Now I have, for example, partial yz, partial st, ds dt, and we've seen this before. We've wanted to, you remember this little notational, little math crime, right? But that's very convenient and always points you in the right direction that we talked about back in chapter 5. Boom, there it is. Kind of cancel those, and that kind of sort of suggests that maybe this whole thing ought to be called dy dz. Now, so we're going to do that. We're going to call that dy dz, and likewise this dz dx, and likewise this dx dy. Some more questions come up. One big question is, but is there any geometrically meaningful sense in which area in the xy plane is somehow involved here? And it turns out that, absolutely, there really is. It's a 15-minute discussion that doesn't make the cut for, what we're going to spend course time on. So you don't need to know that, but if you're curious, I'd be very happy to discuss it with anyone who wants to hear that little 15-minute discussion as to why this makes perfect geometric sense. Anyway, that's highly optional. But anyway, the point is, this is notationally a pretty reasonable substitute for that, aka the ds vector. And so with that in mind, right, just like we did with line integrals, we're going to take this new formula for ds, put it in there. Don't forget that plus minus. Got to worry about that. And reminding that the vector field is coordinates PQR, for example, let's say. Then we can crank out this dot product. And here is our alternative notation for a vector surface integral. And again, it doesn't look particularly helpful, right? If I claim that these are the same, like who would ever choose the one on the right? It's a lot clunkier to write down. Not clear how this helps us. It's just a sort of sort of equivalent. It doesn't really simplify anything from what we already had. You're still going to have to compute the dy dz, dz dx, dx dy based on the parameterization. It's all the same calculations. Why would anyone ever choose the one on the right? And, well, again, so, pretty good reason. This is, roughly speaking, what integrals of differential two forms look like. And differential forms are bonkers powerful. They solve problems that evaded the best mathematicians on the planet for 100 years. This is really cool math, very, very powerful, but it's beyond what we can do in this course, and so we're never going to see the benefits of this notation in this course, and that's just the way the cookie crumbles. The problem, the reason why I have to mention that is that this notation is in common use. Again, because of all that cool stuff, right? So you're going to see that in your futures. can't help it. I'm not the bad guy here. I didn't do it, right? But you are going to see that, and so you need to know how to deal with this when you do see it. And here's what I advise. Make sure to remember this. Well, let me put the minus sign in there. This specific formula for the ds vector. Make sure that you remember exactly which differentials go where, right? And then when you see something like what we have down here, knowing that these are your ds vector, plus or minus, you can see what they're being multiplied by, noting the order. The order matters. The order is very important. And then you can reverse engineer what the vector field is that this is referring to. And again, it's just like we did back with vector line integrals. Same story. Different details, obviously, but strategically, it's the same. Is that cool? Everybody see what I'm talking about? When you see this unfortunate, inconvenient notation, everybody feel like you recognize how to turn it back into something that we know how to work with? All right. Cool. Okay, I guess I ended up talking about that after all. Okay, symmetry theorems. We'll be quick with this one because it's exactly what you would expect, pretty much. And when you're talking about scalar surface integrals, if you have an integrand that is odd and a domain that is symmetric, and I emphasize, you got to have both of these conditions. It's got to be both, and it's got to be. Let's see here, color choices. Oh gosh, I'll use blue. The same plane. Got to be the same plane for both of the symmetries. When that happens, your scalar surface integral is equal to 0 by odd symmetry. And again, it's exactly what you would think. We've seen this for double integrals. We've seen this for triple integrals. We had to recognize that what we saw back in high school in Calc 1 was the same theorem for single variable integrals. We saw it then not long ago for scalar line integrals, right? So this is like our fourth example of an odd symmetry theorem. So a little bit of a yawn. It's true for exactly the same reasons that you would think. So I'm not going to prove it, but I hope it's believable. So again, nice tool. Be on the lookout. Can be useful sometimes. The landmine, the thing that you have to be worried about, this is very important, is that this only works for scalar surface integrals. That is a very big deal. Scalar surface integrals only. If you look at a vector surface integral, for example, like so, there is no odd symmetry theorem for vector surface integrals. And if you make such an argument, then what you're writing down is nonsense. It just is. There is no odd symmetry theorem. Roughly speaking, why there is no odd symmetry theorem is if you look at your ds vector, right, and remind yourself that, let's see here, I'll use blue, that the normal vector, the orientation unit normal vector is part of that. And now let's look at a symmetric surface. Right, this surface is symmetric through that plane. If you'll, play along with my whatever level of artistic confidence I've got here. The areas on each side, you could maybe argue to yourself, those are going to be the same areas, and it's the points are exactly opposite, the reflections of each other and the oddness and all that part seems to work out. But look at those normal vectors. They're not the same. They're also not negatives of each other. They're just different, right? So when you look at this term by term, they just don't match up. And there is no such odd symmetry theorem as a result. Does that make sense to everybody? So heads up, again, this is your job to remember that you can't use it for vector surface integrals. Only for scalar surface integrals. Real quick side note, just a quick cultural point. I have focused my symmetry theorems in this course on odd symmetry theorems. And there are other symmetry theorems. Y'all probably remember from Calc 1 that there's an even symmetry theorem. And I've deliberately not showed you. There is an equivalent in multivariable. I've deliberately not showed it to you because I feel like you can get yourself into more trouble with it than you can get yourself out of. I think it's counterproductive in most cases for students. And here's another few symmetry theorems that I've deliberately not shown you. There is a symmetry theorem for vector surface integrals. And it's kind of cool. And it involves mirror symmetries. Not odd, not even, but mirror symmetries. And it, again, is a pretty cool conversation. And if anyone's curious, I'm happy to show you. But I'm deliberately made the choice not to make it part of the course. I think it's more trouble than it's worth in the great majority of cases. So I think it'd be counterproductive. So anyways, that's a cultural point. Just so you know, there is a cool little clever move that you can pull that makes this work. Okay. Oh, and there's also, I'll just mention, there's rotational symmetries that you can write down. Various other cool symmetries that are out there. And again, in most cases, more trouble than they're worth. Okay. All right, moving along. So, we spent a bunch of time talking about vector line integrals, now vector surface integrals. And both of them are examples of differential forms. And I mentioned that when we were talking about the coordinate notations. It's basically what differential forms look like, is coordinate line integral notation and coordinate surface integral notation. And very powerful, very cool. Not something we're going to do anything with. But so here's the observation I'll make here. Because these two constructions are both examples of kind of the same thing, they're both differential forms, but not hard to imagine then if they're both kind of just different examples of the same thing, you would expect them to have a lot of shared features, a lot in common. And now we've noticed some of this as we've developed. Gone through this. They both have odd symmetry for the scalar version, but not the vector version. They both have these coordinate notations. They both have orientation issues. They both sort of derive out of their scalar cousins by looking at oriented applications, work and flux, right? So sure, we've seen some analogies as they developed, but there's a lot of analogies, and that's what I want to focus on here. There are a couple of reasons for me to show you this. One is, again, just kind of cultural interest, right? I mean, I think it's good to know what's out there, even if it doesn't, help you with the plug and chug computation, just so you kind of have a little bit more lay of the land. I think that's valuable. I mean, you do that in other courses, right? Do that kind of thing in history courses and, what have you, right? So one is just, it's just kind of neat to see deeper realities reflected in what we see. But there's also a pedagogical reason, and that is when you see all these analogies and all these sort of like patterns, noticing the patterns makes it easier to remember the stuff. Right? That's how the brain, we notice patterns. That's how we think, and very often, a lot of cases. So, there is a bonkers strong pattern here, and I want y'all to see it, again, if only for the sort of the pedagogical, memory purposes, but also I think the cultural stuff is really cool. So, anyway, in both cases, line integrals, we parameterize the curve. Surface integrals, we parameterize the surface. In both cases, we take what I'm going to call a derivative. The derivative of a parameterized curve is a velocity. Okay, now here I have to stretch things a little bit. What kind of a derivative do we take of a parametric surface? Well, I'm going to call capital N a derivative, and it is not exactly, right? But it is a cross product of partial derivatives. It comes right out of derivatives. So it's kind of analogous in some sense. Okay. And now look at how these show up in these established equations that we have down below here. And I emphasize now all these equations at the bottom of the page, nothing new. We've written all that down previously. This is just sort of a terse summary, kind of a compact summary of various relationships that we've talked about in these contexts. And notice that the V and the N, both of which are derivatives of the parameterizations, show up in analogous places. It's kind of wild. Okay, oh, by the way, while we're at it, let's note that size in the domain, in the pullback domain, length dt there, area dt ds there, show up in analogous places in the algebra. Okay, well, let's see here. Output size. We can talk about the length of that little piece of curve. We can talk about the area of this little piece of surface. Those output sizes, again, look where they land in the algebra. Totally analogous, right? I mean, what are the odds? Right? It's not a coincidence. It can't be a coincidence. It's too good. The analogy is too strong. This is not a coincidence. What we are seeing here is kind of, shadows and glimpses of extremely deep facts about differential forms. This is kind of wild. But again, strong pattern, and again, good for remembering. Let's see. Now we also look at unit vectors. We look at the unit vector in the direction of the velocity. That's our t. We look at the unit vector in the direction of capital N. That's our parameterized unit normal, little n. And look where those show up in the algebra. And then let's see here, we have our combined, we have our dr vector, our vector differential, dr, that points in the direction of the orientation and its magnitude is the size. And then we have our ds vector, our surface vector differential, that points in the direction of the orientation and its magnitude is the size, right? Analogous players, look where they show up in the algebra. It's all the same. It's constantly sort of stunning to me how strong this analogy is, how well the claim is that these are really the same thing, same song, second verse. It's all the same stuff. It's just a slightly different context geometrically, right? And that's why we get this very strong pattern. So again, good cultural note, but in terms of rubber meets the road, how are y'all going to use this? You can use what you understand about vector line integrals. And if you understand the analogy, and if which players over here are playing the analogous role to which players over here, to help you understand vector surface integrals. And so, again, I think there's a lot of good to be gained there. By the way, let me point out further, if I can get the computer to cooperate. There we go. This analogy continues. If you take these players and let's see here. Look down into these other equations that we have for work integrals and flux integrals, vector line integrals, vector surface integrals. And I'm not going to go through and do it because it would take time. But if you just go through and continue to look at where these players sit in these equations, the pattern continues perfectly. So, kind of wild. And I encourage you to look through and think that through and recognize the strength of that analogy. Okay, thought you'd find that to be cool. And we move along. So we're done with 7.2 now, moving along into 7.3, Stokes' theorem and Gauss's theorem. By the way, just for a little context, again, I know y'all are mostly engineers. We in the math department have had many conversations with Pratt about, okay, what do you need your students to know, right? And number one on the list of things that it's important to Pratt that its students know about multivariable calculus Stokes' theorem and Gauss' theorem. It comes up so much. It's unbelievable. A sizable fraction of how electricity and magnetism work, for example. A sizable fraction of that is, I would say, kind of special case, cute little example of Stokes' theorem and Gauss' theorem. And we're going to see a little bit of that as we go through this material. So they're tremendously important. And by the way, it's not just that. If you want to understand fluid flows, pretty big deal, right? And if you want to understand fluid flows, well, these theorems are tremendously important in that stuff as well. So a lot of powerful applications. And we actually have a lot of the tools that we need to be able to develop these theorems already made. By the way, let me remind you, I said a long time ago that the way I was going to approach various theorems in this class was going to be to kind of approach all of the theorems in deliberately analogous ways. Because if you look at all the theorems in a certain special way, you will notice that they all follow the same pattern. And I think doing all these theorems from that shared point of view, following the same pattern, makes all of them easier to understand. Okay. So we approached, for example, Green's theorem from a certain point of view. Just as a reminder, we approached Green's theorem from the point of view of accumulation. Right? That we developed this idea of an accumulating quantity, and look, as soon as you have an accumulating quantity, the whole is the sum of the parts allows you to take a certain point of view that you're talking about a stuff. Not that you actually are, but maybe. But you can certainly view it that way. And if you can view it as a stuff, you can talk about the density. And if there's a meaningful notion of density, then you can integrate to make an integral theorem. And this comes up a lot. Right? Okay. All right. Okay. So, that's what we're going to do here with Gauss's theorem. I'm going to start with Gauss. The book starts with Stokes. I like to start with Gauss. By the way, most multivariable calculus courses do it my way. Not that it matters. Okay, so just like with Green's theorem, we're going to be coming at this from the point of view of accumulation. We have to start, just like with Green's theorem, with this idea of a boundary and what is the orientation on a boundary. Right? So going forward, now remember we already made this point, going forward, boundary means oriented. That's an oriented construction. You have to know the convention of how to orient boundaries. Okay. All right, so here's the convention. Arbitrary, but standard. When you have a solid region, like this region R here, solid region, and I put an air bubble in it for reasons you'll see in a second. And if you are looking at a point on the boundary, keep in mind the boundary is kind of the dividing area between what's in the surface and what's in the solid and what's not in the solid. Right? It's the border between yes in the solid and no not in the solid. And the rule is whatever point you're on, let's see here, choosing, okay, the orientation is always away from the solid. So like so. All right, so you look at this purple point up here. That purple point, if I go as indicated by blue, I'm going away from the green region. If I were to go in the opposite direction, I would be going into the green region. The arbitrary, full confession, arbitrary, right? But highly standard, by the way, highly connected to all of the other arbitrary conventions that we've chosen. So we really have to stick with these standard conventions. Standard convention is away from the solid. Okay. Now, a lot of people like to oversimplify. By the way, flashbacks to Green's theorem. Remember with Green's theorem, there was this thing about the regions on your left, blah, blah, and everyone likes to say counterclockwise. But it isn't. It isn't always counterclockwise. Sometimes that's clockwise if you're like in the inside and there's little weird special cases. Same story here. The oversimplified take that people give on this is to say it's oriented outward. It isn't always outward. Very often it is, sure, but it's not always. So for example, at a point like this red point down here, on the part of the boundary of the green region, that's kind of the sort of the air bubble part of the boundary. Notice that away from the solid is not outward. That's kind of inward. So be careful with that little oversimplification. Again, you oversimplify, you start to make mistakes, and everything crashes and burns. Beware of that one. Pausing. Questions? Everybody see what the rule is? Okay. Next step, just like we did with Green's theorem, is to think about accumulation. After all, if we're going to make an accumulation argument, we'd better identify an accumulating quantity. And it had better have that feature of accumulation. The whole had better be the sum of the parts. So now a quick observation I'll make. Now, because we're in 3 dimensions now, we're going to talk about accumulation over volumes. This is not a case where we're going to take areas and chop up the area into pieces and see if the whole is the sum of the parts. It's not what we're doing. We're going to be looking at solid 3-dimensional regions, solid 3-dimensional volumes. Looking at splitting up the volumes, the 3-dimensional region itself. And on those volumes, we're going to talk about whether the whole is the sum of the parts. Okay. So here we go. I claim that boundary flux accumulates. Here's the picture. By the way, that picture might look familiar. Y'all remember this picture from chapter 6. We had talked about boundary flux. We played some game with Green's theorem where you rotate 90 degrees and check some details, and you get the 2-dimensional divergence theorem. Yeah, or you can just notice that boundary flux itself is an accumulating quantity, and we talked through the details of that way back then. So here, we just have kind of a 3-dimensional version of basically the same thing. So looking at this big volume, if I chop it and look at the left piece, well, the boundary flux, keep in mind, boundary says you got to look at the boundary of whatever thing you're talking about and then talk about the flux through that boundary. Right? That's why we say boundary flux specifically. Right? So whatever 3-dimensional region, look at the boundary, oriented as standard, and then look at flux through that boundary. Okay, so that said, let me go back to a consistent coloring. Looking at this green region, the boundary flux would be like this on that left region R1. Yeah? Is everybody cool? That's the boundary of the left region, and that's the outward orientations on those boundary pieces of that left region. Now let's look at the same thing on the right half. If I look at this right half, and again, let's look at the boundary. The boundary is these two pieces. Now again, oriented outward, loosely speaking. So oriented like that, and that's the boundary of R2. And now is the whole the sum of the parts? And well, I mean, just like with Green's theorem, I think you can see that the big question is these two computations on this shared face, and on that shared face, right, on that shared face, we have two flux integrals over the exact same surface, but with opposite orientations. So they're exact negatives of each other, and they cancel. And it's the exact same thing that we saw back with this case. Here we had not a shared face, but a shared edge, which as part of D1 is oriented that way, part of the boundary of D1, that is. As part of the boundary of D2, is oriented that way. And that shared edge, we're looking at fluxes, again, on the same surface, edge, and again with opposite orientations, which are again negatives of each other and therefore cancel. It's really, really similar to what we're doing here. It's just three-dimensional now instead of two. Is everybody okay with that? You see how it's geometrically very analogous? I mean, different dimensions, but very analogous. Okay, so all that disappears. We have an accumulating quantity, and now we just jump on to the ride we've already created. Once you have an accumulating quantity, okay, well then we can view it as stuff. Once you have it as stuff, you can talk about the corresponding notion of density. And once you have a density, and I'm going to go back and talk through the details, right? Once you have a notion of density, right, then you can compute stuff as stuff per unit volume times volume, and out comes a theorem. So, using the same strategy, this whole idea of an accumulating quantity, free result, right, in several steps that comes out of just us noticing that you have an accumulating quantity, and the result is Gauss's divergence theorem, which you see here is some of y'all may have seen some version of this previously, but a boundary flux on the left being computed as a triple integral of divergence on the right. Now let's go back and do the details. I just wanted you to see where this is going. And let's see, let me clean up the mess. Okay, so accumulating quantity. Accumulating quantities behave like stuff. Now, I do want to say a couple of quick words about this as stuff, and I want to recognize when I say it behaves like stuff, I'm not saying it is a literal physical stuff. Well, of course not, right? But it plays like it does. It behaves as if it is, and it's a weird take. It's counterintuitive because we measure it on the boundary, right? That's how you compute flux, boundary flux specifically. It's literally flux through the boundary. It's computed on the boundary. I'm making this outrageous suggestion that this thing that is computed on the boundary is actually distributed throughout the interior somehow, or that you can reasonably choose to view it that way. And I know that's strange, right? So I am going to remind you, we have seen this before. And I'm going to remind you, specifically here, when we were talking about the fundamental theorem of calculus, we made this observation here. Same story. Let's talk about change. Change is computed by looking at a formula on the endpoints. F of B minus F of A. That's how you compute how much something changed. That computation takes place entirely on the boundary, right? The endpoints of that interval. And, if you didn't have experience with how stuff changes, right? The process of things changing, you might look at we got this weird formula called F of B minus F of A, and it's clearly computed on the boundary, and now they're telling me that it happens on the interior, and you could imagine that you might find yourself a little uncomfortable with the claim that change happens in the interior. But of course it does. This is where the change is actually happening, and look at it. There it is. You can watch the function change. Right, so I love this example because it dispels this idea that my weird ask is nonsense. Right? I know it sounds kind of like nonsense, but it sure isn't nonsense here. Computed on the boundary literally happens in the interior, real stuff. Right? This is a very reasonable point of view here. And any accumulating quantity you can view this same way. It's just harder to draw the picture. when I claim that flux measured on the boundary can be viewed as kind of a stuff distributed through the interior, just like change is. Yeah, it's harder to see the picture, but it totally works. Okay. All right. Again with density, let's talk about density. In the same way that we view mass density as being mass per unit volume, flux isn't the same as mass, but it behaves like a stuff, kind of like mass, and so we can talk about flux density, boundary flux density in kind of the same way. And recall, flux, boundary flux, computed on the boundary, outward oriented. That flux is a kind of a stuff. And when we say flux density, we literally mean flux per unit volume. And if, as I claim, flux behaves typically as a kind of a stuff, all right, stuff per unit volume. That's what a density is. Is that cool? Now, again, just like with Green's theorem, we're going to find ourselves with some notational sort of options and some terminological options. So flux density, by the way, is, in my physics classes way back when, flux density was the most common term that I heard used to refer to this. It is, however, also called divergence. And they all remember that from chapter 3, back in chapter 3. And I made this claim that I couldn't justify at the time, but I made this claim that divergence somehow represents how the fluid is kind of expanding outward away from wherever you're computing it. And, well, I think that arguably makes sense now. Because look at, if you're willing to take my word for it, that when you compute flux density, the formula is divergence. It's exactly this. Literally, flux is measuring the extent to which the fluid is flowing in the outward direction through the surface. It's literally an outward flow. And so flux per unit volume, and you take a limit as volume goes down, and it's going to kind of, in some sense, measure at each individual point, to what extent is there a spreading out of the fluid. And I think that pops from this point of view. So that's why we have this claim. By the way, a couple of other notational reminders. Divergence sometimes written as div. Also, divergence very often written as del dot. Right? Very common choice of notation for divergence. Okay. All right. Okay. So we are so close, and I think I have here. Oh, I've got 2 minutes left. Okay, so this is we're going to totally be fine here. Before we get into the theorem, I just want to emphasize this take that I have up here, right? That this formula, divergence, literally, by telling you the density of flux, is literally telling you where flux comes from. So in the same way that the derivative tells you where change happens, right? If you want to understand, if you want to get your hands algebraically on the fact that there's clearly more change happening there than there is there, well, if you want to know where change is happening, you look at change density, aka the derivative, and you just notice that at that point, literally, there is more change because the change density is greater. Right? And the change density just straight up answers the question for you. And the exact same thing happens with flux density. If you have a vector field that results in a certain amount of flux, computed on a boundary, of course, and if you want to know where that flux is coming from, honestly, really, which points get the credit more than other points for where that flux is coming from? Yeah, if you want to know where the flux is coming from, you look at flux density. And at this point B, the flux density is greater, and so therefore there's more flux coming from that point B. And close enough. We'll go ahead and call it there. See y'all later. We're right on the edge of being able to write down the big theorem. Okay, see y'all later.